Welcome to video 3.6. In this video, I'll be covering beta sheets, the other type of secondary structure other than alpha helices in protein. Now, looking at beta sheets, keep in mind that like alpha helices, the goal here is also to fulfill the backbone H bonding, just like the helices did, right? To make a regular stable structure that again we call regular because we see it all the time. However, there is a key difference. Right? Beta sheets are made of separate strands, connected by regions of a regular secondary structure. So let's break that down, first by visiting what the alpha helix is. Recall that the alpha helix was a period of the primary sequence that folded into a weird spiral, right? You never saw an alpha helix here and here, right? You could have a helix and you could have a different helix, but they're never going to be combining, right? A helix is in one place and it folds into a spiral. Let's compare that to beta sheets, right? With beta sheets, we can actually have the sheet forming in two distinct different locations. Here's sheet 1 and here's sheet 2. As we follow the N-terminus, we see that sheet 1 and sheet 2 form together to form a beta sheet, right? So it's actually two different strands. It's the same original sequence, but it's two different parts coming together to make the beta sheet. This was an example of when they're close together, but they can also be far apart. Right, looking at this sequence, starting at the N-terminus, we have sheet 1, and then there's a period of extended secondary sequence, right, of just, irregular structure, and then we run into sheet 2. And those two sheets, again, form the beta sheet. So keep in mind that with beta sheets, it's not just one place in time. Like it is in alpha helix, you can have multiple different parts of your protein coming together. Also keep in mind that here I've only shown two strands, but beta sheets can become beta pages. They can become very big. They're still called beta sheets, but don't call them beta pages. Here's an example, right? Sheet 1, 2, 3, and 4. You can see that as we follow the N-terminus, we have 1, swings back into 2, swings back into 3, and swings back into 4. And all of these form one large beta sheet. Right, so clearly they're a little more complicated than alpha helices, but there's not too much more to understand. Again, the backbone H bonding, it's critical to understand that that part is satisfied. That's why these structures form. So, with that in mind, let's break down beta sheets into two different classes. First is the parallel beta sheet. The important thing about the parallel beta sheet is that all of the sheets, or all of the individual sequences, are in the same direction. So I say N to C direction. So here's an example. We start at the N-terminus and we go here. So this is N to C, this way. We loop back around, and you notice you're going to see these loops. We loop back around and we go here, N to C. We loop back around, N to C. So all of these sheets are oriented, they're moving in the same direction. That is what we mean by a parallel beta sheet, right? Now, these are connected typically by, I'm going to call them loops, because you can see in order to have them be in the same direction, you need to have some, more amino acids, more primary sequence to go back around and loop back around to make them line up perfectly. Alternatively, you have the anti-parallel beta sheet. Here, sheets alternate in direction. Right, so we start with the N-terminus and we move. This one is N to C. And here we have a very quick turn, right? It could also be a big elaborate thing that connects, but typically you see these quick turns. And now this is going N to C. So you can see how they're no longer lined up. Another quick loop, N to C, as we go to the C terminus. So you can see that those sheets are no longer in the same direction. We call these hairpin turns. Again, it's not a requirement that anti-parallel sheets have to be connected by hairpin turns, but you can see that it's very easy to do, right? Boom, boom, they're close in sequence. It's just a quick turn because you're going the other direction. Again, when you're in a parallel scenario, you can't just go here because then you'd be going the wrong direction. So you have to loop all the way around. That's why you see those big loops. Now, there's one important thing, right? We've talked about parallel and anti-parallel in regards to the directions of the protein sequence. but be careful not to confuse that with the direction of H bonding. With parallel beta sheets, where they're going in the same direction, you actually have slanted H bonds. So it can be worth just memorizing that it's not what you would expect, right? The H bonds here between the groups, and I'm not going to draw the full chemical structure. Your lecture notes, I'm sure, will have, and other online images can do that. I'm here for ideas, not specific details. But the bonds that you make, these are going to be H bonds that are slanted, right? So parallel means the H bonds actually aren't parallel. Funny enough, when you have the anti-parallel beta sheets, so that direction is quickly turning, the H bonds themselves are actually parallel H bonds. So be careful when we talk about parallel and anti-parallel, we're not talking about the H bonds. We're talking about the direction of the sequence. You can remember that anti-parallel beta sheets, when they have quick hairpin turns and go the other way, have parallel H bonds, where parallel beta sheets have slanted ones. With that out of the way, let's do a quick overview question for all of secondary structure. Feel free to pause the video and identify all of the secondary structures listed. For beta sheets, make sure you identify if they're parallel or anti-parallel. Great, so for this question, we can go from N to C. Let's do this beta sheet first, this big red one. So we can see that we're going down and we have a quick hairpin turn, so these are anti-parallel to each other. And if we keep following the sequence, we're going down, then up, then down. So this whole thing is now an anti-parallel beta sheet. Right, the whole thing can be called a beta sheet, even though the first two parts are connected by a hairpin turn, and then this third part is connected by a much longer thing. Overall, you can see they're all going in opposite directions. That is an anti-parallel beta sheet. The other beta sheet over here, if we take a look at the sequence, so if we follow the end sequence all the way here, we're going this way, we do a big loop, and then we go this way. So they're both lined up with each other. These are parallel beta sheets. Then this and this are simply alpha helices. Right? We don't have any information about what those amino acids are in this question, so I can't say if they're, polar or nonpolar, hydrophobic, hydrophilic. All I know is that I drew a spiral shape, therefore they are alpha helices. With that in mind, right, all the black lines are just irregular secondary structure. They're important, but we don't see that name of alpha helix or beta sheet. In the next video, we'll go to the final stage of protein structure, which is putting it all together, basically, and tertiary structure, folding into the true 3D shape of the protein. Again, that shape determines the function, so getting up to this point is important. Let's pull it all together in the remaining videos. I'll see you there.